All right, happy snow day. Today, let's take a look at evaluating some definite integrals. Okay, we've already talked a little bit about this notation here, but let's put a few more vocabulary terms to it. All right, so this right here, okay, is our integral symbol, okay, or integral sign. There is not some special name for this symbol, it's just called an integral sign. Then if we are evaluating a definite integral, that means we're finding the area under the curve. Okay, we've talked about that already, starting at this x value and ending at this x value. So if we want to actually give some vocab terms to those are called the lower limit and upper limit of integration. All right, then the actual function that we're finding the area under is called the integrand. Okay, and then this tells me what variable I'm integrating with respect to. All right, so the way that we would read this whole thing is the integral of f of x from a to b. And we say, when we find the area under the curve, okay, or find the value of the integral, we have evaluated the integral. Okay, so let's practice a few of these simple ones. Okay, I'm just going to kind of make up examples as we go here. So let's say we want to evaluate the area under the curve from 1 to 4 of 7 dx. Okay, so 7 is my function. All right, so we're talking about just a horizontal line here. So if we graph this, let's see, 7 will be right here. So I'm taking this function, and I want to evaluate it from 1, 2, 3 to 4. So what I'm doing is finding this area right here, okay, this area under the curve. So this is just the area of this rectangle. So this rectangle has a height of 7, right, because this function is y equals 7, and a width of 3. The difference between 1 and 4 is 3. So the area here, the answer to this integral would just be 3 times 7, 21. All right, so we can just write our answer just like that. Okay, this integral is equal to 21. All right. Let's see, how about you guys try the area under the curve from -1 to 4 of 3 dx. All right, so if we graph this, our function is at 3. It's just this horizontal line here. And we are evaluating this from -1 all the way up to 4, right? So I'm finding the area of this rectangle. So the height of this rectangle is 3. Its width would be 5, the difference between -1 and 4. So 5 times 3 gets me that this is equal to 15. All right. So whenever we're evaluating the area under a constant function, it's pretty simple. Right? We're just going to get a rectangle. All right, let's try something a little different. How about the area from 0 to 3 of x dx. Okay, so now my function is y equals x. So if I graph this, y equals x is just the line with a y-intercept of 0 and a slope of 1. So this is what my line would look like. Right, so I can make a nice straight line there. So if I want to evaluate the area under this curve from 0 to 3, what we're doing is, well, we're starting here, and then 1, 2, 3, going to here. So now I'm evaluating this area here. Okay, well, this is a triangle. The area of a triangle we know is 1/2 base times height. So my base, this distance would be 1, 2, 3. My height would be 1, 2, 3. So this is going to be 1/2 times 3 times 3. So that gets me 9/2. Okay, so the area under y equals x from 0 to 3 is just the area of this triangle. So we can use other geometric shapes other than a rectangle to find the exact area. Okay, now this is the exact area. This is not an approximation. Okay, sometimes we are able to use geometric formulas to find exact areas. All right, let's try another one. How about the, let's just do x plus 1 dx from 1 to 4. All right, so now we graph this. All right, so we know that this line has a y-intercept of 1 and a slope of 1. So we're going to look like this. So let's graph this. So my line will look something like that. And now I want the area under this curve from 1 to 4. So from here, 2, 3, 4 to here. And so this area under the curve. What shape is that? Okay, that's a trapezoid. So I want to find the area of this trapezoid to find the exact, or to exactly evaluate this integral. Well, we know the area of a trapezoid is 1/2 times the height times the average of the two bases. So remember, the height is the distance between the two bases. So I'm saying this is 1/2 times the height. My height will be this difference, 4 minus 1, which is 3. And then my two bases, okay, will be these sides right here. Okay, well, since I have this graphed, I can just count and see that this side would be 2, and then this side would be 5. Okay, or I could plug these values into my function, just like we did for our trapezoidal approximations. Okay, so then I'll have 1 plus 5 over 2. So let's see, we end up with 3 times 3 times 1/2. 9/2. All right. Whoops, I messed that up, didn't I? That should not be a 1. That should be a 2. So 2 plus 5 over 2. So that gets me 7/2 plus 3/2 would be 10/2. So 5. And I apologize. I just messed that all up, didn't I? All right. Let me start this over. Okay. So the area of a trapezoid is the height, which we said was 3, times base 1 plus base 2 divided by 2. All right. So we get 7 halves times 3 is 21 halves. There we go. That looks a little better. I apologize for that. So, you guys try one here. So let's see. Evaluate the area from 2 to 4 of 2x dx. Alright, so let's graph this here. Alright, so this is a line with a slope of 2 and a y-intercept of 0, so we're starting here and going up by 2. So this line will look like this. So I want the area under this line from 2 to 4. So from here to here. So I'm finding the area of this trapezoid here. So area of a trapezoid is the base, or I'm sorry, the height. So the difference between these two x values, which is 2, times the average of the two bases. So my two bases would be 4 and 8. So times 4 plus 8 over 2. So that will get me an area of 12. All right. Now, let's jump to this idea. Okay. Now, everything we've done so far, every example, our curve has been above the x-axis. Right? Whenever our curve is above the x-axis, the area between the curve and the x-axis is positive. If my curve ends up below the x-axis for some part that I'm interested in, we say that that area is negative. Okay, area beneath the curve. Okay, and that's what this is saying. Whenever our function itself is negative, so that's area below the x-axis, we say that that area is negative. So if we want to evaluate a curve, okay, where we end up with both positive and negative areas, we just take the area above the x-axis minus the area below the x-axis. All right, so an example of this, all right, if I take the area from -1 to 2 of x dx, all right, if I graph this, all right, I'm going to make my scale a little bit bigger here. So let's say this is -1, 1, 2. So this is just the line y equals x. So if we graph this line, get something like this. And now I want to evaluate this from -1 to 2. So what I end up with is two different pieces. Okay, I'm finding the area from -1 up to 2. So I end up with two different triangles here. Okay, this area here, okay, below the x-axis is negative area. All right, so it wouldn't hurt to maybe make a note of that. Area above the x-axis then is positive. Okay, and notice I'm taking the area between the curve and the x-axis. Okay, sometimes I see students try to take the area between the curve and the y-axis. Right? That's not correct. Okay, make sure you're taking the area between the curve and the x-axis. So here we need to find the area of these two different triangles. Okay, we'll take this one as positive, this one as negative, and combine them. So the area of this first triangle, okay, will be 1/2 the area of this first triangle would be 1/2 times 2 times 2. Now, times 2 times 2. Okay, and now, since this is below the x-axis, we say that this is negative. Okay, and now I'm just going to add then this piece. Now, we can always do this, and we'll take a look at examples even when we know how to find areas of under ugly curves. Okay, we can split areas up into multiple pieces. So then, oh my goodness sakes, my scale messed me up. All right, this area, that's 1 and 1, not 2 and 2, the way I defined it. All right, so then plus 1/2 times a base of 2 times a height of 2 over here. So we get negative 1/2 plus 2, which would be 3/2. So we get the area of this piece is negative 1/2. The area of this piece is positive 2. Therefore, our total area here we say is 3/2. All right. Now, you guys try one of these. So let's say we want the area from let's just say from 1 to 4 of x minus 2 dx. Alright, so if we graph this, this is a line with a slope of 1 and a y-intercept of negative 2. So I'll go back to a normal scale here. So my y-intercept is down here at negative 2, a slope of 1, so my line will look something like this. Alright, now I want the area under this curve from 1, so right here, up to 4, so right here. So I'm finding these areas. So this actually ends up being the same as the last problem, right? This area right here, since it's below the x-axis, would be 1/2 times 1 times 1, but it'll be negative since it's below the x-axis, so that area would be negative 1/2. This area would be 2 times 2 times 1/2, so 2, so plus 2. So we get that this total area is 3/2. All right. Now, the last thing that we're going to take a look at today is getting rid of some numbers. So let's say I want to evaluate this integral, say from a to b of 4 dx. Okay, so I'm still thinking, well, I want to graph this function. So I'm graphing this function. That's the horizontal line through y equals 4 right here. And now I want to evaluate this from A to B. I have no idea where A and B are. I can really put them wherever I want. Okay, but this is just kind of a visual of what's going on. All right, so let's see, we'll label this as 4. So the height of this rectangle is 4, but the width, okay, I don't know the width. I don't have numbers for the width. What I can say the width is just b minus a. So what I can say that this is equal to is the height of 4 times the width of b minus a. Right? And we could distribute the 4 through and say it's 4b minus 4a, but I can just leave it like that. Okay, 4 times the quantity b minus a. All right, let's try another one. How about the area from S to 2t of our function 2x. Okay, well, if we graph this, right, we know that this is the line, the y-intercept of 0 and a slope of 2. So it's going to look like this. And now I want to find the area from S up to 2t. So I'm finding this area. Now this is a trapezoid, right? So my area of a trapezoid is the height. So here the height is the difference between these two. So that difference we can just say is 2t minus s. So my height is 2t minus s. Now I need the bases. Okay, the bases are these two parallel sides. So here we can't just count boxes on the graph because we arbitrarily placed this s and 2t. So what I need to think about is plugging s into my function. So if I plug s into this function, I would get 2s. So this base here is 2s. Now if I plug 2t into my function, I would have 2 times 2t. That would be 4t. So we would say that this base has is 4t over 2. So this is, we can just leave it like this. Okay, we could multiply it out, but we can just leave it like this. My height times base 1 plus base 2 divided by 2. All right. I'm going to have you guys try one here, and then we will be done. All right. So how about the integral from 2 to b of x plus 1 dx. Okay, give this one a try. All right, so if we graph this, we know the function x plus 1, slope of 1, y-intercept of 1. So that's going to look like this. And now this tells me that I'm starting at 2, so it gives me a definite value to start at, but then some arbitrary value to end at. So again, this will end up being a trapezoid. So the area of my trapezoid here will be the height. Okay, so my height would be b minus 2, the difference between these bases, times these bases. So here I can actually get this height. If I plug 2 into my function, I get that this height is just 3. Plus, and then if I plug b into my function, I would get b plus 1. So I can say plus b plus 1 over 2. All right, there is a Math Excel up. It is same type of questions as this, so give that a try, and we will talk about that in class on Thursday. It is due before class starts on Thursday, though.